right.
Okay, so welcome at another Origin seminar today. Today we have a talk by Michiel Lambrechts, who did his PhD at the Lund Observatory in Sweden, after which he did a 2-year postdoc at Nice Observatory, and now he's back again at Lund Observatory. And he's going to give a talk about protoplanets and planetesimals. So the floor is yours.
All right. So let me share the presentation. So this should be okay, I think. Oh, sorry. Yep.
Yeah, looks good.
All right, good. Yeah, so hi everybody. I'm Michiel Lambrechts. I'm a postdoc in Lund University. I'm very excited to be part of this Origin seminar because I do want to talk about how super Earths form and what this tells us about terrestrial planet formation, so our origins. It's work done together with many people, especially the second part of the talk is a lot of work done together with Sebastian Lorik, who is another postdoc here in Lund. And then there's other collaborators like Seth Jacobson, Anders Johansson, Alessandro Morbidelli, Bertrand Beach, Sean Raymond, and Andre Isidoro. Okay, just to get started, just a few words on super Earths. To be clear, I'm going to use the term just to describe planets with masses intermediate to the Earth and Neptune. And if you look at the planets found by the Kepler satellite that are in this figure projected as if they were orbiting the same star, so to say, you see that there are actually a lot of those planets with radii between 2 to 4 Earth radii. And in very close in orbits, that is to say, you can see here the orbits of Jupiter, Earth, and Mercury. So most of these planets are inside the orbit of the Earth. In fact, if you do the statistics right, you find that about 1/3, maybe a bit more, of all solar-like stars host super Earths within 100-day orbits. But we have no super Earth in the solar system. The question is why? Another way of phrasing that question is, are super Earths just scaled-up versions of terrestrial planet formation? And with this, I mean, are those close-in super Earths, did they just form similar to the terrestrial planets, except that they formed in an environment where there was more mass available? And to be a bit precise about what we mean with terrestrial planet formation, I mean that is basically the formation of rocky bodies at moderate orbits, or like the Earth, about 1 AU, that grew to completion after the protoplanetary dissipated. That takes a few million years. And then through planetesimal collisions, and specifically by repeated giant impacts between Mars-mass embryos, something of that sort, they grow to completion. They reach their final mass. That's sort of illustrated in this small cartoon. You start with a bunch of Marses, and by repeated giant impacts, you form ultimately Earth-like planets. And of course, we have a signature of at least one such late collision, and that is the moon-forming impact. But such a scenario does not take into account something that we have learned more recently, that is that protoplanetary disks are filled with pebbles. And pebbles are millimeter to centimeter size small particles that form in these disks through small collisions. And in this small picture here shows TW Hydra. And you see this basically millimeter emission from this disk, revealing those pebbles on scales that are about 100 AU. So really the full disk is filled with these pebbles. You can then do this exercise for different star-forming regions. And now you can learn something about what is the initial mass budget in these protoplanetary disks and how it decays with time through radial drift. Right? So these particles don't keep growing. At some point, they start drifting inwards. Here you have time in million years. Here's the mass that is characteristic for such disk in young star forming regions. So for example, if we start with Perseus, which is a very young star cluster, you see that the average disk masses are very high in excess of 100 Earth masses. In fact, we know about HL tau, which indeed has about maybe 200 to 300 Earth masses of such pebbles, but that's a very massive disk with a gas mass that exceeds a tenth of a solar mass. But TW Hydra is also such a massive example where there is probably about around 100 Earth masses of pebbles. But typically, it seems that over time, the mass reservoir decays. So with a disk lifetime of a few million years, you find that after a few million years, you have about 10 to maybe even an Earth mass of pebbles left. So roughly speaking, you can say that there is a radial flux of about 100 Earth masses of pebbles per million years, and an exponential decay is not an extremely bad fit, although you can make better pebble-drift models that do better. Okay. Then, interestingly, through numerical experiments, we have learned that streaming instabilities can operate in these protoplanetary disks that can concentrate spontaneously large clumps of these pebbles, which then can collapse under self-gravity into planetesimals that are like 10 to 100 kilometers, even larger in size. And finally, these largest planetesimals can sweep up the remaining pebbles in the disk to a process that we call pebble accretion. So I will say a few more words specifically on pebble accretion. Okay, so the mechanism here is that we have a seed, so like this planetesimal here, and a bunch of pebbles on the same orbit, but that are radially drifting inwards and also with respect to this planetesimal azimutally. And when such a pebble encounters this planetesimal, this is sort of the interaction that you have. Basically, because of gas drag, this orbit is dissipated and you quickly get accreted. And that's different for this gray particle, which represents a particle that does not feel gas drag, so you can think of a planetesimal. This one simply gets gravitationally scattered. And so we get here to the essence. The pebbles have an increased cross-section, and that's what we are interested in. You can simplify this even more with an analogy that I use to explain what I'm doing at work all day to my 5-year-old son. So basically, you have centrally a planetary core, which is this black marble. It's embedded in a potential, and pebbles kind of come in with an approach velocity here, and then they encounter the potential. There's friction, which dissipates the orbit, and they get accreted on top of the central object. So these marbles are here, the pebbles by analogy. And so you see, you can fast forward a little bit, and you see that the object grows in mass. It's a very efficient process. Here's a figure that illustrates if you want to grow a core to 10 Earth masses, how long it takes you to do so at different orbital locations. And you can see that planetesimal accretion is relatively efficient, especially if you go into wider orbits, while pebble accretion is a very efficient process, allowing you to form within a million-year timescale large planetary cores. Right? So this is the time to grow to 10 Earth mass as a function of the orbital radius. If you think it's interesting, there's a whole bunch of references here, and there's the Johansen and Lambrechts annual review if you really want to get into the details. All right. But we were actually focused on forming super Earth systems, right? And what we want to do is make a simple model that starts with rocky embryos that are moon-sized inside the iceline, and which is an initial condition that we typically use for classical terrestrial planet formation. But then we want to include 3 key physical processes. One is the embodied part, let's say scattering and merging of planetary bodies. But we also want to include type 1 migration and eccentricity inclination damping, which is because we want to study specifically what happens inside the gas disk phase. And of course, pebble accretion. And we do this in a relatively simplified inner disk model with an inner disk age at 0.1 AU and exponential damping time scale of 1 million year, okay, for both the gas and the pebble disk. But we keep one parameter free, and that is the amount of pebbles that enters this, let's say, terrestrial region. So the pebble flux is the free parameter. And you can think of many reasons why the pebble flux would be different between different systems. For one, protoplanetary disk might be different. Here, there's a big disk with a big pebble reservoir driving a large pebble flux. You could be in a smaller disk with a smaller pebble flux, or you could end up in a disk like here, where there's an outer giant planet that blocks the outer reservoir of pebbles entering the inner disk. So one could think of many reasons why the pebble flux would be different, and we keep that as a free parameter. All right. Now, this is the result. In a way, here we have on the x-axis the semi-major axis on the logarithmic scale in AU, and here we have the mass of the bodies in Earth masses. And we start, for example, with looking at the growth tracks of these blue bodies here. This is the case where we integrate pebble flux. The integrated pebble flux is about 110 Earth masses. You see the effect of pebble accretion that drives the mass growth, and the bodies grow to a few Mars masses in size. There's not so much migration because the bodies are small, and we have no merging event. It's actually a very quiescent system. Then we change the pebble flux by less than a factor 2, right? So integrate it's 190 Earth masses. And again, we see initially the effect of pebble accretion, grow the embryos large. But then something special happens. When they reach Earth masses, migration becomes very efficient, and the bodies migrate all the way to the inner disk. And there you get merging events, which causes these growth tracks to become discontinuous. Right? So this is the difference depending on the pebble flux. You can do is there a question?
Yeah, Michiel, I was wondering, so Jake and I are mouthing off in the chat section. I wonder if you could set us straight. There are some questions about efficiency of pebble accretion, right. Stokes number.
All right, so I have to find a chat.
I could just repeat it verbally.
Yeah, could you just repeat it? Yeah.
So I was wondering, you said Stokes number in your model is like 10 to the -3 or so.
Yeah.
And I was wondering if that would be too small because it would be strongly coupled pebbles to the pebbles would be strongly coupled to the gas. And you said it would be potentially more efficient in terms of fraction of pebbles captured. So I thought the Stokes number like 0.1 for 1 is the best for, roughly for losing angular momentum rapidly and accreting.
Yeah, it turns out if you just express it as a filtering fraction, so just as the ratio of what you accrete versus what drifts past you, you actually benefit going down to smaller particle sizes in the regime of interest.
Okay.
Of course, that does break down at some point. For one, at some point you really get into like you're just really too coupled. And the other one is also that unfortunately, when you go down to smaller sizes, typically your particle scale height goes up as well. So you're longer in 3D accretion, and that's also a way of actually strongly reducing. So the real statement is it helps you to go to smaller sizes if you don't increase your pebble scale height by a lot, which then requires a very quiescent disks and so on. So yeah.
Okay. Thank you.
Yeah, we can get back to that later. Yeah. Okay. So okay. Then you can do this for a whole bunch of systems instead of just one. For the low pebble flux case, it doesn't matter so much. The accretion was so ordered, so the embryos just remain spread across the disk as they were. Of course, if you do it for the systems that got more massive, then you see indeed that different simulations give different results because there's a feedback on accretion through these mergers. But something maybe is striking is that these bodies don't grow larger than basically 10 Earth mass, and that is because the upper masses are regulated by the pebble isolation mass. What do I mean with that? Well, it is if the gravity of the core becomes sufficiently large to perturb the gas disk, then this core kind of drives small pressure bumps, which is sort of shown here, kind of increased density. And this sort of shallow gap perturbs also the gas velocity. And it perturbs it in such a way that when it is originally subkeplerian, it basically gets pushed down to Keplerian velocities. And that takes away the reason for particles to radial drift inwards and thereby halts solid accretion onto the core. Actually, it does something else. It's not only that it blocks the flow onto the body itself, it also blocks the flow of pebbles to all the other inner embryos. So this is an important implication. Another implication is that it's also a good point to identify when gas accretion becomes more important, but that's a separate discussion. Just for your entertainment, so to say, you can actually relatively quickly get to sort of conceptual understanding of why this pebble isolation mass exists. That is, there is a subcapillary velocity of the gas. That's why the pebbles are drifting in. And then you can express the perturbation at the gas scale height away from the planet in this way. So this is from a paper from Vution in Suka in 2009. And basically, you see you have basically gravitational perturbation at a gas scale height away from the core. And if you then equate those two velocities, you find that there's this isolation mass that is very dependent on the gas aspect ratio, but when you're sort of at like Jupiter-like 5 AU distances, it's probably somewhere between 20 Earth masses. In our case, for the inner disk, it's actually around 10 Earth masses. So that's the reason why bodies don't go larger. All right. So yeah, this is what the picture looks like at the end of the gas phase. But of course, one wonders what would happen next. So that's what is shown here, where we advance these simulations with an additional 100 million year of evolution. In this case, all these systems basically become unstable. And in the blue case, the low pebble flux case, you see that multiple merging events happen between these Mars embryos, leading up the formation of up to 5 Earth mass plants. So it is relatively reminiscent of this kind of classical terrestrial plant formation mode that I talked about earlier. Also, for the super Earth system, some merging events happen. And an important other effect is that basically all the instabilities in these systems break the resonant chains. So what do I actually mean with that? So initially, pebble accretion makes very compact, tight systems. And that you can see here, expressed in mutual Hill radii. They're all very tightly packed around 10 mutual Hill radii. In fact, they're all also resonant. And that you can see here. So here we plot for each pair the outer and the inner periods. And you can see, for example, focusing here on the orange line, the cumulative mass fraction of planets that have these period ratios. And you see that many of these systems are in 5:4, 4:3, 3:2 configurations. And then when the disk dissipates and these bodies kind of relax to their final state, you see these resonances are broken and you get a much more widely spaced system that actually is pretty reminiscent of what we find in the Kepler system. So the Kepler system's period ratio distribution is here shown in the dashed green line. In fact, if you analyze the simulations, we also find multiplicity is quite good. They're all around this kind of four planet systems, and we also have a pretty decent eccentricity inclination distribution that seems to agree with the Kepler system. So we get a picture that is pretty consistent with what we understand of super Earths today. All right, so now I want to summarize, let's say, the first part of this talk. And that is that basically in the same physical model, we see a transition, all right? So the super Earths form when the pebble flux is sufficiently high for protoplanets to grow to the pebble isolation mass. That is what you see here. And we can recover terrestrial plant formation mode when this is not true, right? When the embryos do not grow so large, they don't migrate to the inner disk mesh, and we recover this kind of terrestrial mode. The exact transition points, of course, depends on what are essentially the disk parameters. It is around 100 Earth masses for these parameters that we explored, but as I said, it depends, for example, on the particle size, the pebble gas scale height, temperature profile, and so forth. I show this cartoon here on the side because I want to emphasize that we have two different types of planetary systems, our super Earth system and terrestrial planetary systems, but they can be understood as different outcomes in uniform scenarios. You don't need different scenarios for different outcomes. And that's somewhat reminiscent with a bit of imagination with evolutionary biology. Okay, it's the same process at play, but sometimes an external stress, for us, it's the pebble flux, causes divergent outcomes. Okay, now I want to focus in what is coming next a little bit more on this terrestrial growth mode. So basically these systems here. But start a little bit on this started with sort of moon-massed embryos. I wanted to now to really go down to the planetesimal stage and look a little bit also more in the context of the solar system. So now we're moving gears a little bit. And I think this is a very interesting question in the sense that we sometimes think of terrestrial planet formation as an almost solved question. Well, I think it's very much of an open question. So first off, let's start with what I mean with protoplanets, exactly. So with protoplanets, we mean here in this talk, the largest embryos that form within a few million years in the gaseous protoplanetary disk phase, okay? So in the classical terrestrial planet formation scenario, these are basically then the bodies that undergo a giant impact phase that can last for 100 million years, resulting in the final terrestrial planets. But it's interesting that from cosmochemistry, we don't actually have strong constraints on how large the Earth grew. For Mars, we are pretty certain. Proto-Mars probably completed its growth in the gas disk. But for Earth, it could be anywhere. So this is based on hafnium tungsten dating of core formation. It could basically be anywhere between Mars and up to basically near complete Earth. So we don't actually have a strong constraint on this. And moreover, we also don't really theoretically understand terrestrial planet formation very well, I would say. So this is a real nice plot from a paper from Kevin Walsh and Hal Levinson that shows how planetesimals drive growth, but that one does not necessarily reach this oligarchic growth stage with Mars mass resulting in Mars mass embryos everywhere, that people often assume to be essentially the initial condition for the terrestrial planet formation simulation. So here you see, it's also a paper by Carter et al. 2005. So here you see the growth. Initially, things start off well, but even after a few million years, you can see that growth is essentially just too slow, even starting with 3 Earth masses of 100 to 1,000 kilometer sized planetesimal, so basically like the MMSN, too slow to reach the mass of Mars at a Mars-like orbit. So this is a real problem. All right. So this brings us to the question also directly of what should we actually assume for our initial planetesimal mass distribution. This is me here. It's like, where, when, I don't know. So instead of answering these questions, we'll make a few big assumptions and explore 2 scenarios. Okay, so that's here on the left-hand side of the slide. Okay. The first thing is that we will assume that there is an early planetesimal formation burst. Let's think really early in the beginning of the protoplanetary disk phase, around, let's say, 10 to the 5 years. Okay. There's some arguments to make in favor of this. For one, you have the ages of the achondrites, right? So they're probably very young. There's also other reasons. If one, for example, thinks about refractory depletion in non-carbonaceous chondrites, you can also make a story that there must have been a primordial population that was more refractory rich. That's recently proposed by Alessandro Morbidelli. And there are also theoretical reasons why it might be plausible that we have very early phases of streaming instability. For example, this is from a paper by Johan Appelgren, who's a PhD student here in Lund. And he looked at when disks can have like streaming instability prone regions. And you can see that you can even have these at very early stages, right? And then presumably there's also a later formed protoplanetary population, which we, in this case, I'm going to assume that this one does not play a big role in plant formation, but that this one is sort of the initial seed of starting plant formation. Now, there's also different assumptions one can make about the spatial distribution of where you put those planetesimals. There's a good case to make. I think that the first planetesimals form around the iceline. That's something that Chris Ormel has also investigated in the context of the TRAPPIST super Earth system. But then you also have other papers, for example, by Joanna Daszkowska, that go exactly along these lines. There's also the other picture where you can think, well, maybe the planetesimal formation is still a little bit more stochastic than we think, and you'll go back to more kind of classical terrestrial planet formation, where you say that it's sort of spread around the terrestrial planet formation region. So this is like, for example, also something that Halevison explored in 2015. Then for the initial planetesimal masses, for now, we're going to keep it simple, and we're going to just say that they are Ceres-mass. And this is based on scaling relations for the streaming stability simulations to get the top of the size distribution. And in a paper by Liu, we explored how exactly to transform these kind of typically numerical results in code units back to real units. Turns out a Ceres-mass object is sort of what one could expect at the top end of the distribution. So this is what our initial conditions are going to be like. If you think that's interesting, here's a small commercial break. We are organizing a planetesimal formation meeting virtually. It's 17 November. You're all very welcome to register and have a look at the program. I'm not going to say much more, but if you think this sounds cool, have a look. Okay. So this brings us to, okay, now we need to do this complete growth model from planetesimals to planets. Okay, again, we need embody, we need pebble accretion, we type 1 migration, but the embody part here is non-trivial because we really need a large number of initially planetesimal-sized objects. Okay, so for this reason, because we want to go into simulating like 1,000 Ceres-sized orbits, the 1,000 Ceres-mass bodies, sort of basically 2 Mars masses in total. To simulate this, we turn to GPU methods. Okay, so we're using actually code, it's called Genga, that was developed by Simon Krim in 2014, and we've added there now pebble accretion routine, which is not completely trivial because pebble filtering is basically global operation, so one has to do the parallelization somewhat intelligently. But basically, this buys us a 10 times speed up compared to just serial embodied codes, and which makes this basically doable. Okay, yeah, basically this is, so that was just me standing next to a GPU computer being very happy about this. All right, let me, can I stop this for a second? Okay, okay, so basically I just want to say, so now I'm going to show simulation starting from such a narrow annulus of planetesimals, these 0.2 Earth masses of planetesimals that we put on very compact ring around 1.5 AU, and then we explore how mass grows. And this is a small inset that shows a bird's eye view of the same process. So let me just do this. So this is basically what happens. All right. So to have a closer look at this, so there's actually a lot of things going on, but one can break it roughly down again into sort of like 3 main things. First, this ring is, let's say, relatively unstable, and that you have a lot of initial planetesimal spreading very early on, and collisions, right? So the violent collisions between these bodies causing mass doubling, and the first larger bodies emerge in this way, so through collisions. But then, as embryos grow larger, pebble accretion takes over. So pebble bodies that are in this mass regime, they see their growth really accelerated by pebble accretion because like larger bodies accrete actually more efficiently. And then when they grow to this kind of super Mars sizes, migration becomes very important, and these bodies migrate towards the inner disk, towards 1 AU-like distances. All right. Why is that? Actually, it's not so trivial, and it has to do with that only a few bodies grow large. Actually, there is not so much competition, and that is because initially only a few lucky bodies have undergo a few collisions and maintain basically orbits which have low inclinations, which continuously put them inside the pebble midplane. So that's what you see here. It's only a few bodies that manage to basically remain in the pebble midplane. Most of the population gets excited on high inclinations. And it's these bodies, that go early first and actually happen basically by chance to remain in the midplane. These are the ones that grow efficiently, and they grow large. In the end, the largest embryos do not accrete more than 10% of their total mass through collisional merger. So initially, it's important to make a few big seeds, but after that, they just sweep up all the pebbles, and their mass is ultimately completely dominated by pebbles. So you can see this here. So these are the few largest embryos in the simulation, the ones that go to Earth masses, and you can see that the contribution that they have through mergers is basically very, very small, right? Less than 10%. Okay. So this is actually an encouraging picture. Okay, we form larger than Mars mass embryos on protoplanetary disk lifetimes. So a big win. Actually, interestingly, we form large central embryos, a bit reminiscent of the Venus-Earth pair, and small Marses. But not, these are the pluses, but not all is, is well, so to say. Because there is also an obvious problem here. It's me again wondering what the hell is going on, because we don't form Mercury, right? One of the planets in our solar system we don't form. This is, by the way, a set of hadrons, so it's really statistically, it's very difficult to get something over there. Okay, so that's why we explore another scenario, and this is this white belt case, and we'll see if this does any better. So I'll play the movie. Okay, so this is basically what it looks like in this case. So this is a simulation that is essentially the same parameters as before, but a few things are different, right? So the planetesimals are now spread between 0.3 to 2.8 AU. Okay, so it's a really wider belt, and but it has the same total mass. It still has 2 Mars masses in total. So this is actually very small mass compared to classical terrestrial planet formation, which is Earth masses of planetesimals. Now we have a small caveat, is we reduced pebble scale height here to 0.01. So it's a very, very narrow disk scale height. So it's nearly laminar disk. And now we look for 1.5 million evolution. As you look here, you can see that basically the same mechanisms are still at play, right? So first, we have collisions, a few bodies grow large. Then we have pebble accretion, which really makes some embryos to sort of winner take it all, grow large. Okay. But you can see also something interesting here, and that is that actually the mass distribution is a bit better here, in the sense that now we do get sort of these Mercury type embryos. And if you look at a set of 8 runs showing the 6 largest bodies, you can see that indeed we produce this kind of solar system terrestrial-like plant configuration with centrally concentrated large bodies, Earth size, and then Mercury, Mars-sized bodies on the outskirts. So what is actually going on here? Okay, so now we're going to look a little bit more in detail. So here I plot the cumulative pebble flux. So this is basically how much mass has entered inside the terrestrial system, which is like better said, passes through the terrestrial system as pebbles. Okay, and then you can look at the mass of the protoplanets. So you see they start out small, some collisions, and then they grow and reach their final mass. The dashed line here is the total mass in planets. Then for illustration, I also show some gray lines here, which are some bodies that remain small. Okay, so some of the remaining planetesimals. And then here in the bottom, I show let's say the mass fraction, so how large they've grown with respect to their final mass. So for example, these gray bodies here, they grow initially very quickly by some combination of planetesimal collisions and some pebble accretion, then they get high inclination. Essentially, their growth stalls and you don't see much growth. We can also look at, say, this Mars mass embryo, which only grows large relatively late. You can see that most of it does basically from the last 2 Earth masses of pebbles that enter in the terrestrial planet formation region. While Mercury, this body that grows early, actually has a little bit of a different growth. It grows early, it grows fast, but then it gets competitive accretion from the outer embryo. So less pebbles actually make it all the way here. So filtering is actually pretty efficient, which stalls the growth of this inner Mercury body. So that's why these bodies don't grow large anymore. Okay. Now we get to the implications of this. Okay. One interesting thing is that the pebble flux may change composition in time. Okay, we don't know the exact details of this, and for sake of argument, I will simplify it by a lot and say that we likely have a pebble flux that goes from sort of refractory to more volatile, starting from sort of a non-carbonaceous chondrite-like composition to one that is more carbonaceous-like. That implies, in our case, that Mars-like and Earth-like protoplanets that complete their growth relatively great would also accrete a significant fraction of this late volatile CCL-like pebble flux. And interestingly, that is maybe also the case. So possibly the Earth is composed out of, let's say, 40% of the CCL-like material. That's a paper by Warren from 2011. And it's also sort of a scenario that's advocated by Schiller et al. In 2018. Still, I want to stress that it's actually relatively interesting that this, for example, Mercury-like protoplanets probably have a relatively different composition. For one, they form from collisions with refractory rich planetesimals, right? From these early non-carbonaceous, very early planetesimals. And they also only accrete from these early refractory rich pebble flux, because afterwards it's basically filtered by the outer embryos. That's why they don't grow larger than Mars mass. And they also undergo a lot of collisions, basically. Some also could drive volatiles. The point I want to make here is that protoplanets accreting from the same pebble flux do not necessarily end up having the same end bulk composition. Okay? So it's not that because you have transporting the same kind of continuous pebble flux that all these pebbles have an ultimately the same composition. Okay, so here is then a picture for a plant formation scenario. Very broadly, you could think of disk first forming. So very early on, it forms and expands outwards. That means a fraction of the pebbles immediately start drifting inwards, presumably this more refractory component, this non-carbonaceous component. Another fraction is kind of viscously expanded outwards and only drifts in later. Not all the material of the outer disk presumably reaches the inner disk, because at some point Jupiter forms and probably reaches pebble isolation mass and cuts the pebble flux for these bodies going inwards. And ultimately, you leave with a terrestrial system, which maybe only remained terrestrial because indeed the pebble flux at some point was cut by Jupiter. I'm not the first to propose this. There's a lot of papers here, but we try to make this now really kind of, let's say, more quantitative scenarios. This is basically the big picture. Just before we start wrapping up, I want to say a few words about the late giant impact phase. Okay, so you form these terrestrial-like systems. What happens next? Well, that actually is, in the context of the solar system, not so easy to answer. The short answer is we don't know. Do you know yet? Okay, but it requires a careful dynamical study, including the presence of the outer giant planets, which are not in these simulations right now, because they can, of course, trigger dynamical instabilities. Think about the NIS scenario, or even Grand TAC, but in general, the presence of giant planets is pretty disturbing, either directly by triggering direct dynamical instabilities or by cleaning up the planetesimal distribution surrounding it. So, just for illustrative purposes, I show 2 continued runs of this set, and you can see that actually in this case, okay, there's actually 2 very quiet systems. Actually, not much happens either, both in the narrowing broad belt simulation. These bodies remain pretty much where they are and remain relatively low eccentricities and inclinations that are not so much unlike what we see in the solar system right now. Okay, but still, this is very preliminary. Okay, so now I'm getting to the summary. This is actually a sunset on Mars. Okay, and although it at first is pretty impressive, it is actually also extremely boring. especially if you compare it here to a sunset in Lund that I took a picture of. And of course, this connects directly to this talk in the sense that even in our own solar system, we have such divergent outcomes of planet formation, which makes it a really, I think, fascinating field of study. And of course, hope that this work aids in trying to understand why, right? And so let me go then now through what I try to convey. Okay, so what we did and what we looked at. Okay, so we performed embodied simulations of planet formation that show how protoplanets located within the iceline. We focused really on the inner disk, can complete their growth by pebble accretion. Okay, it's an important process at play that is one of the two others. Namely, initially, certainly planetesimal and protoplanet collisions are very important and presumably also late. And type 1 migration, very important, also making distinction between the super Earth systems and terrestrial ones. All right, I think this scenario naturally explains the origin of compact super Earth systems that go to completion before gaseous dissipation. The resonant chains are naturally broken after this dissipation. I think that's sort of the picture for the super Earths. Then interestingly, when the pebble flux is reduced, okay, an initial lower mass pebble disk, outer giant planets halting the pebble flux, we can recover a terrestrial planet formation mode. Okay, and we verified this with planetesimal to protoplanet embodied runs. So we do the whole formation process. What we show is that firstly, we resolve an outstanding issue that is basically related to the required formation of Mars-like embryos within a few millennia. So we can do that. But we also find as an implication that the terrestrial protoplanets may grow to near completion in the gas disk phase. Okay, so this is a real possibility. And then the exact nature of the giant impact phase that follows, frequently how unstable, that still remains to be investigated. And in the bigger picture, of course, what we try to do is develop a coherent theoretical framework to understand both terrestrial and super Earth formation. And I really think this is a key tool that is needed to contextualize what is going to come. And the future is our hunt for terrestrial habitable, like terrestrial-like, and however adjective you want to use. But this is what we're going to find and hunt for in exoplanets. And we need to understand what we are actually talking about. Okay, so this is the end of my talk.
Thank you, Michiel, for a great talk. Well, everybody can unmute now if they want to and give an applause.
Thanks.
Okay. So everybody that has a question, you can raise your hand in the participants chat, and then we can go through questions. I can see that we have a question from Gijs.
Hi, Michiel. That was a great talk. So, so I really find this dichotomy between the super Earths and the terrestrial planet mode formation very interesting. But I also have a question about that. So what about planets that are terrestrial planets in size, or like Earth size, but like much further in, like at an orbital period of a few days? Because those systems also exist. So like in your models, like do the inner planets always be big and the outer planets also small, or is that something that you can address?
Right. Yeah, that's a super interesting question. I think I might actually have a slide on this. Well, yeah, it's basically this, right? So yeah, so your question is about basically this population, like very short orbit, small mass planets. I think it's super interesting. I don't have a very good answer on this, except that firstly, I think this picture shows that like the mass and radius distribution is actually, well, let's say the mass distribution is probably relatively continuous, okay? So although we have a photon gap here that really has to do with the density, separating rocky versus the not rocky ones, the ones that have hydrogen helium envelope, presumably. So, but the underlying distribution is probably relatively continuous. So that connects to the idea that, okay, there is just a scenario and one has maybe different outcomes, but it is part of the same thing. But you are completely right that, of course, this is a bit puzzling. Part of it is, of course, that there is a strong relationship between the how big the planets grow is set by the pebble isolation mass. So, for example, one thing which maybe I also have a slide on. Yeah, here. is, for example, the correlation with stellar mass, just to name one, but this could also be different for other reasons. But like just taking the stellar mass, that has a strong implication also on pebble isolation mass. And that is, I think, something you just see also in the data. Like if you go to smaller mass stars, you really find smaller mass planets. And if you take, for example, this TRAPPIST system here, although they look very terrestrial in masses, or their Earth mass, they presumably formed as super Earths. Like they're this compact chain that migrated inwards, did not go unstable as opposed to many other systems, but probably it's just basically they're super Earths. So even though they're Earth mass in size, they follow that growth mode. So that's at least, for example, part of an explanation why some systems might remain small, other might just be relatively cold disks, for example, and it's a very strong dependency on HFR. So these are maybe some explanations. Yeah. But it's super interesting. I really it would be cool to investigate more.
And we also have a question from Joanna.
Hi, Michiel.
Hey, this is like an amazing seminar. You have no idea who's selecting.
I'm spying from Europe. So yeah, like, great work. I liked basically very impressive about connecting the n-body and pebble accretion. I think this is like what everyone is waiting for, right? And so I just wanted, like, you have this like super beautiful graphic with the formation of the solar system, like somewhere close to the end. Could you come back to that?
Right. Yeah. I mean, I went just like,
you probably like just spent the week doing this or something, but it looks amazing.
No, I mean, it's just like when you go 3D in Keynote, I mean, it's like,
So I think my question would be, where does the in the initial condition, where is the difference between the NC and CC reservoirs coming from? Is it like some sort of iceline or something like this? And how far back it is in the disk if like it arrives at the terrestrial planet region only after some significant time, right?
I I wish I knew. Okay, I think it is. My impression is that the consensus now is that it is probably inherited from an inhomogeneous distribution in the core. So basically, I actually also have an additional slide on this. I think here. Okay, so for the people who are not so familiar with this, maybe I can actually go through this very quickly. If you analyze meteorites, you find that one class on isotopically, so not even chemically, just really on the isotope level, is very distinct from the other ones. So here you have the non-carbonaceous ones, and these are the carbonaceous ones. You see these in these isotopes like chromium and titanium. But you also see it in like things like calcium, which is another way of looking at the same thing. Interestingly, the Earth and the Moon sort of, and Mars, Earth and Mars sort of fall in between those two reservoirs. So they presumably accrete a bit of both. Okay, so now I simplified it by a lot. The carbonaceous chondrites basically are enriched in R-process nuclei. So they probably have some sort of supernova contribution that the other reservoir did not have. And so presumably maybe that was incorporated in the cloud and the dust in the initial cloud that later formed the solar system disk. I think there's also an option that is a form of thermal processing. So if, like, for example, certain grains have sort of a preference for certain type of isotopes, and then when there's a very violent environment, the protoplanetary, so maybe something happens to those dust particles that get close to the star initially, and those become NC and are not CC anymore. Right? The carbonaceous chondrites are really, in any ways, the sort of more pristine one, with the CI chondrites being like the really absolute, like basically chunk of the sun, like primitive material. So I don't know. I think these are the two options, and my feeling is that it is initially a spatial distribution, either through say outer injection or thermal processing, maybe both, that then later gets translated in a time evolution, where initially you accrete from the inner reservoir and later you accrete from the outer reservoir. So that's, I guess, all I'm comfortable about claiming about this. Yeah.
Thanks.
And then we have a question from Andrew.
Yeah, I figured someone in, physically in Arizona should ask a question. In the terrestrial planets, there's obviously a well-known trend in the solar system for the uncompressed densities, going from less than 4 for Mars to greater than 5 for Mercury. I think this is often explained in terms of the sort of giant impact picture.
Yeah.
Seems like if it's the same pebbles drifting by, it might be something of a challenge for pebble accretion models. So I'm wondering what's been done on that.
Right. I think I would have to think a bit about Mars. I don't have a good answer for that right now. Mercury, I touched upon a little bit. I think it might be really a combination of it, that its high density is partially because it comes from a very much more collisional environment, which would allow you at least to some degree get rid of some of the more volatile elements. And presumably also because it forms early, it also forms from the more refractory component, and which is also the more high density environment. And just think of being about like in a very, very close to maybe 1000 Kelvin, where basically only the most refractory species could survive. So no, I think that's another component would be super interesting to look into. I think sort of the next thing to do, but one would have to really trace down more carefully the composition and the impact history of these bodies.
Anyway, I'll also just add to that for the being in Arizona part, we actually have, I think, even more interesting sunsets than farmlands in Sweden. But
Andrew, you can show any picture if you have one.
But the point there was more to show that we have a sun in Sweden. It was not so much what was in the picture. It was just that there is sometimes a sun, like that one day in the summer.
And I think there are also some questions that people asked in the chat window as well.
Right.
Yeah, we've got a question from Zachary Adam in the chat window.
Yeah.
I can read it.
Yeah.
Is there any coupling or correlation between rapidity of protoplanet formation and later stage parameters that might be critical for life's origins or habitability? So such examples are timing of volatile release to the surface from the mantle or formation of differentiated crust.
Yeah, that's super interesting, but I think that's like even taking, in a way, it's taking Andrew's question even a step further. And when you really start connecting the sort of like compositional evolution of terrestrial plant formation to life, which is, of course, a valid question to take. I think this falls a little bit out of the scope of this project. In a way, to be very crude, we're just trying to form Mars to begin with, and are happy that we also can form relatively nice Earth protoplanets. Like this is the stage we're in. But that's like super cool way to go ahead. I don't think I have a very concrete answer. It's it's a good question for in the chat. Like I should maybe think about it and write something back. But maybe there are other questions in the meantime.
And there's a question from Mariana, who is asking about is type 1 migration incorporated in the model once the protoplanets reach the mass of Mars? Like is type 1 migration dependent on the protoplanet mass then?
Yeah. So the migration rate is very much dependent on the mass of the body. You can think of it, it's in a way, it's a back reaction thing. So like the bigger the mass of the body, the larger, the more it perturbs the surrounding gas disk and the spiral waves it triggers, then back react on the body, and that causes a torque on this body, making it move. So a small body, sub-Mars, basically does not feel meaningful migration, right? although it's a little bit more of importance for like eccentricity, inclination damping, it actually will not change its orbit much. But as soon as you read any speed storing function, as you can see, let me see if I can. Yeah, for example, here you can really see that as bodies grow larger than Mars, suddenly these growth tracks, instead of just going up happily, so that means that the accretion goes basically faster than the migration, so you're just moving up here. But here, even though you're accreting at very high rates, pebbles, you still migrate a lot. So that causes this strong tack, let's say, or move to the left in this figure. So it's very important.
Okay. Well, more questions are still coming up. I'm not sure how much time we still have left.
Yeah.
Yeah, we can still ask 2 more questions. Vladimir and then Tim. And there was one comment by Sebastian.
Hey, Michiel.
Hey.
Great talk.
Ah, thanks. How are you doing?
Doing fine, yeah. It's warm and bright here, unlike Lund, I suppose.
Right, yeah.
Right. I was wondering, though, you were saying, well, I mean, like from your talk, it seems that everything that depends on the pebble flux.
Yeah.
Right. And the pebble flux is a function of the pressure gradient, the disk mass, right? The star mass.
Yeah.
Like all of the things that go into it. So my question is, do we see observational evidence that super Earths form preferentially in some systems, but not others? And in a way that we can connect that to a higher pebble flux?
Is super good question. I don't know if there's an easy way to do it, but one way is maybe through looking at. I mean, this is sort of more like on the top of my head kind of stuff, but like it's to look at binaries, like stellar binaries, which at least for the ones that and look at the occurrence rate around binaries in the sense that relatively compact binaries, let's say ones that are separated only by 30 AU or so, they can presumably, let's say, the primary or so, does not have a disk that extends outside of the orbit. So that really gives you an idea of what basically the range of the primordial, the maximal possible range of this primordial pebble disk. And in that way, if the mass reservoir, I mean, then you know crudely that it must have a mass reservoir that is so and so, and then you can look at the occurrence rate of super Earths given the sort of separation and presumably the mass distribution. And you do find that at some, as far as I understand, at some radius, you do really find that the occurrence rates of super Earths really go down with the stellar the separation between the binaries. So this is maybe a way of like observationally looking for evidence about where the critical pebble mass reservoir of the critical pebble flux is. The other way is to do it based on the relation to the occurrence of wider orbit giant planets, like the systems where Jupiter-like planets form that could halt the flux of pebbles, really result in lower occurrence rate of super Earths. That does not seem to be the case. So this goes a little bit in the opposite direction. But I think we have to be careful here. I think for the solar system, my feeling here is for the solar system, Jupiter did play a role. It prevented the pebble flux that ultimately created what became later the Kuiper belt, basically, like a large mass reservoir of planetesimals that did not enter the terrestrial planet formation region. I think the reason is Jupiter. So I think we really can thank Jupiter for being, like Earth. But in other systems, maybe Jupiter-like planets form relatively late. Okay. And if they form late in the evolution of the protoplanetary disk, they don't really cut the flux of the pebbles in a meaningful way, and it does not mean anything. In fact, you could even argue that when you find such a system with a wide orbit giant planet, oh, that's a system where cores could grow large, so there's a high chance that it also in closer orbits you form super Earth. So I think that's a more complicated question, but super interesting. I mean, yeah.
Yeah,
we have also like,
Sorry, you can put.
No, I mean, I was just going to joke that one of the interesting info that I got also from this talk is that Tantan is Belgian. I always thought that he was French. So.
Oh no! Oh, come on, man. I'm glad I set the record straight on this.
Thank you very much.
Yeah.
Then we have another question from Tim.
Michiel, another one from the same side of the pond. Thank you for the really great, insightful and clear talk.
Thanks.
Yeah, so I had a question which was asked which went a little bit the same direction was asked earlier. So on this plot and on other in the videos you showed, I think you form roughly these planets, Earth-sized planets, on the order of 1 million years or so, right? Which is also the same time scale which you would need for this Jupiter barrier to form. On the other hand, you also showed this plot which kind of shows the formation of carbonaceous chondrites up to 4 million years or a bit later even. So what do these planets do from 1.5 million years, 1 million years until the end of the solar disk lifetime?
Yeah, I think, yeah, that's like a fantastic question. I don't have a good question on this. I think for the purpose of this talk, the aim was just to sort of like the aim was just to sort of like paint a picture on how these protoplanets could form, and I did not particularly want to fine-tune exactly matching the solar system. It's more about the general process of terrestrial planet formation. So we did not want to go down that road of really like matching the Earth exactly forming at 3 million years, which basically requires you to do a large parameter study and run large suites of runs to find the good systems. So I think it's plausible to find this in parameter space, the good fit, so to say, and that's of course something we want to do next. That being said, my feeling is, especially if you go into look at sort of models with the disk queens, I think that there is actually a phase in the inner disk where basically a relatively rapid depletion of the inner disk, presumably also held by Jupiter forming a gap, so that basically you could have some more gas-rich evolution in the outer disk while the inner disk is already depleted. And so I think this is maybe a way of kind of freezing in what you do early, relatively early, within like a few million years, or maybe even 1 million years inside the order of Jupiter, and not losing everything by migration. Still, that's to be investigated. For the outer part, in principle, you can collect a lot of material there. This dissipation is there, a very nice mechanism to kind of naturally trigger the formation of all these carbonaceous chondrites, specifically to the end. So yeah, maybe I think that's maybe my vision towards really addressing that in a better way.
All right, thank you.
Yeah, I think there's also kind of different views in cosmochemistry on that, right? So for example, like I think the sort of like Cryer people really want Jupiter to form very early, at least separating the flux very early, in 1 million year. So then the Bizarro group is somewhat more relaxed about this constraint and allows somewhat more time. So I don't think this is also exactly, let's say, a cosmochemically settled issue.
Yeah, I mean, you showed also the evidence for that inner NC chondrites form early, right? So I guess you need to somehow bridge this time scale, even whatever the interpretation of this is. So, but okay, all right.
Yeah, I mean, it's also done. Yeah, exactly, and I think. Yeah, sort of like, for example, yes, okay, my big arrow kind of makes it looks like it really goes very cleanly from carbonaceous to carbonaceous chondrites, but of course, these magmatic irons, then you see apparently maybe there were places in the disk where apparently simultaneously really formed really distinct kind of planetesimal. So, okay, but maybe we don't understand the magmatic iron ages very well, and so on and so on. I think so.
Thank you.
Yeah.
Okay. I think all the questions are done. There are still a couple comments in the chat, but that's, I think, people sharing some papers about the discussion just now.
All right.
But I would like to thank Michiel again for giving a great talk. And I hope to see the rest of you next week again at our next Origin seminar.
Right. Yeah. Well, thanks. I did not have a chance to go through the chat. Should I do this now or?
Yes, please. And then I can send you the chat as well. Caitlin, if you have a comment, would you like to speak? Then please go ahead. But I can send you the chat.
Okay, thanks.
No comment from Caitlin.
Okay, I see.
I don't know if Octavio wants to comment on his paper with Venturini et al.
Yeah, right. Yeah, I'm good. Yeah, it's interesting by Caitlin. It seems to be hard to do it the way I described it. Okay, all right. Too bad. Okay, but in the future, okay, good. Okay.
Just a matter of time. It's just a little.
Just a matter of time. All right, all right. That's exciting.
That there isn't a trend. It's that other than for the hot Jupiters, there's not quite enough to.
Right.
But I think you're certainly right. In principle, we will eventually be able to do that test exactly as you described.
Yeah, it would be awesome. Yeah, cool. All right. Thank you, everyone, for all the questions. And yeah, email me or find me on Twitter these days or something if you have any more questions, I would say.